Trigonometric identities, or the identities of trigonometry. Identities are really just definitions in the form of equations. Since identities are definitions, some of them are pretty obvious. Just to give an example from real life, the equation 1 minute equals 60 seconds is an identity. And from this very obvious identity, we can develop another identity by dividing both sides of this equation by 60. And that is that 1 second equals 1/60th of a minute. So we took a very obvious identity and using basic algebra created another identity, perhaps one that is not quite so obvious. Here's another example that we can pull from the unit circle, and it's pi radians equals 180 degrees. And using this basic identity, we developed that 1 radian is equal to 180 degrees divided by pi. And by dividing it out, we get that 1 radian is approximately equal to 57.296 degrees. And also, that 1 degree is equal to pi radians over 180. So we took one definition or identity and used it with a little algebra to develop some more identities. We're going to do the same thing next, but using the trigonometric ratios. Now we'll get to what you probably tuned in for, the trigonometric identities. The trigonometric identities stem from the first 3 basic trigonometric ratios, and this is what I use to help me remember them. And it's this mnemonic device. Some old hippie caught another hippie tripping on acid. Here, some old hippie becomes sine theta equals opposite over hypotenuse. Caught another hippie becomes cosine theta equals adjacent over hypotenuse. And tripping on acid becomes tangent theta equals opposite over adjacent. And these 3 definitions use the sides of the right triangle given one of the non-90 degree angles. And here in the lower left of the triangle, there is the angle theta. We could be evaluating the other angle in the upper right corner, but I like to, when I can, arrange for the angle being evaluated to be in the lower left corner of the triangle for the sake of consistency. Relative to this angle, theta, the opposite side is the other side at the right triangle on the right side. And of the remaining 2 sides, the short side, in this case at the bottom of the triangle, is the adjacent side, abbreviated ADJ. And the remaining side, the longest side, or the hypotenuse, is labeled HYP. Now we'll define the reciprocal trigonometric ratios. The reciprocal ratio to sine theta is cosecant theta, which is abbreviated CSC theta. Since the cosecant is hypotenuse over opposite, it's the reciprocal of the sine function. The reciprocal ratio to cosine theta is secant theta, which is abbreviated SEC theta. Since the secant is hypotenuse over adjacent, it's the reciprocal of the cosine function. And finally, the reciprocal ratio to tangent theta is cotangent theta, which is abbreviated COT theta. Since the cotangent is adjacent over opposite, it's the reciprocal of the tangent function. These 3 ratios together we call our reciprocal ratios because they are the reciprocals of sine, cosine, and tangent respectively. But these ratios lead to identities. The sine of theta is 1 over the cosecant of theta, and its related identity, cosecant theta equals 1 over sine theta. We have the identity cosine theta equals 1 over the secant of theta, and its related identity, secant theta equals 1 over the cosine of theta. We have the identity tangent theta equals 1 over the cotangent of theta, and its related identity, cotangent theta equals 1 over the tangent of theta. So these 6 identities together I call the reciprocal trigonometric identities. Let's develop another identity, one I call the tangent identity. Let's look at sine theta divided by cosine theta. We can see that sine theta equals opposite over hypotenuse, and cosine theta equals adjacent over hypotenuse. And so sine theta over sine theta equals opposite over hypotenuse over adjacent over hypotenuse. And since dividing by a fraction is the same as multiplying by its reciprocal, this equals opposite over hypotenuse times hypotenuse over adjacent. Hypotenuse over hypotenuse cancel to equal 1, so that leaves us with opposite over adjacent. And where do we see opposite over adjacent? We see it over here to the left. So we end up with our tangent identity, and that sine theta over cosine theta equals the tangent of theta. So we now add the tangent identity to our list of identities. And related to the tangent identity is the cotangent identity, and that is that cosine theta over sine theta equals the cotangent of theta. Now we're going to move on to another trigonometric identity. Let's look at the Pythagorean theorem, a squared plus b squared equals c squared. From here, we're going to transition to the trigonometric version of the Pythagorean theorem, and it starts with adjacent squared plus opposite squared equals the hypotenuse squared. I hope you can see that this is just the Pythagorean theorem, but just using adjacent, opposite, and hypotenuse for a, b, and c. Now we're going to divide this trigonometric version of the Pythagorean theorem by the hypotenuse squared. And here's the equation divided by hypotenuse squared. And hypotenuse squared divided by hypotenuse squared canceled equal 1. Now we'll place adjacent squared over hypotenuse squared and opposite squared over hypotenuse squared inside parentheses and raise to the power of 2 outside the parentheses. And what do we see here? Do these terms look familiar? They should. We see that this first term, adjacent over hypotenuse, is the cosine theta, and that the second term, opposite over hypotenuse, is sine theta. With this identity, if you know what sine theta of any angle is, you can find the cosine, and likewise, if you know the cosine, you can find the sine of an angle. Do you notice that the squared sign is just in front of the thetas? This placement means that each whole term, cosine theta and sine theta, is squared. It can be written this way instead of placing the squared sign outside parentheses. Let's briefly demonstrate how these trigonometric identities work. For that, we can get to our unit circle. Up here on the circle, at let's say 80 degrees, we place a point to form a right triangle on the unit circle. And using this point, we can draw legs of the triangle and a hypotenuse to form a right triangle. And using a right triangle, Pythagorean theorem language, we have the right side or opposite side A, we have the bottom or adjacent side B, and the hypotenuse C, which is equal to the radius of the unit circle. But any triangle created using a point on a unit circle has a hypotenuse of 1, since the hypotenuse is the radius of that circle. So this means that if we know either A or B of this triangle, which would be either sine or cosine, we can solve for the other leg using the Pythagorean theorem, since we know that the hypotenuse is 1. We'll use this identity at the end of the lesson to solve for sine or cosine. Now we can create related identities with sine theta by itself and cosine theta by itself. To solve for sine theta, subtract cosine squared theta from both sides of the equation. Cosine squared theta minus cosine squared theta canceled equals 0 on the left side. We bring down sine squared theta equals 1 minus cosine squared theta. Now we take the square root of both sides of the equation. And we now have the related identity sine theta equals plus or minus the square root of quantity 1 minus cosine squared theta. And if we go through the same process, but solving for cosine theta, we have cosine theta equals plus or minus the square root of quantity 1 minus sine squared theta. Now we're going to go back to the Pythagorean identity, usually written as sine squared theta plus cosine squared theta equals 1. And to help us develop new identities, we'll access the reciprocal identities here at the left, along with the tangent and cotangent identities at the upper right. Let's divide the Pythagorean identity by cosine squared theta. Sine over cosine is opposite over adjacent, or tangent, and we developed this with our tangent identity earlier. So this first term, sine squared theta over cosine squared theta equals tangent squared theta. And for our second term, cosine squared theta over cosine squared theta canceled equal 1. And finally, for our final term on the right side of the equal sign, since we know that 1 over cosine theta is equal to secant theta, 1 over cosine squared theta is equal to secant squared theta. Now we box in our newly created identity, tangent squared theta plus 1 equals secant squared theta. Now we're going to place this newly created identity at the lower right and work out on our last identity of this lesson. To create our last identity, we divided everything in the Pythagorean identity by cosine squared theta. Now we're going to try dividing everything by sine squared theta. Sine squared theta over sine squared theta cancel to equal 1. And since cosine theta over sine theta equals cotangent theta, cosine squared theta over sine squared theta equals cotangent squared theta. And since 1 over sine theta is cosecant theta, 1 over sine squared theta equals cosecant squared theta. So we have our newly created identity, 1 plus cotangent squared theta equals cosecant squared theta. Let's review the identities we've covered in this lesson. We've covered the 6 reciprocal identities, we've covered the tangent and cotangent identities, and then we have the Pythagorean identity. And derived from the Pythagorean identity, we have the identity solved for sine theta and also for cosine theta. And lastly, these two derivations, the one with tangent squared theta plus 1 equals secant squared theta, and one where cotangent squared theta plus 1 is equal to cosecant squared theta. Finally, let's use identities to find the cosine of the angle in this triangle. All we know is that the value of the cosecant of this angle in this triangle is 2. The first thing we'll do is get our reciprocal for the sine of theta, and that's sine theta equals 1 over cosecant theta. And using the identity sine theta equals 1 over cosecant theta, we can replace the cosecant theta with 2. So we get a sine theta of 1/2. Now to find the cosine of theta, we'll pull out this version of the Pythagorean identity, cosine theta equals plus or minus the square root of quantity 1 minus sine squared theta. To use this identity, we'll do two things. First, we'll replace sine theta with 1/2. And secondly, since the angle theta is found in quadrant 1, we will have the plus of the plus or minus. So now we have cosine theta equals the square root of quantity 1 minus 1/2 squared. And since 1 over 2 squared is 1/4, we now have cosine theta equal to the square root of quantity 1 minus 1/4. And since 1 minus 1/4 is 3/4, we get the cosine theta is equal to the square root of 3/4. And since the square root of 4 is 2, we can remove the radical from the denominator and just make it 2. So we have the cosine theta equal to the square root of 3 over 2. It so happens that we can check our solution using the unit circle. Here we see at pi over 6 a sine value of 1/2, and here where the sine is 1/2, we see right next to it, to the left, that the cosine is the square root of 3 over 2, which confirms our answer that we got using the Pythagorean identity. So we box in our answer is correct. This has been Trigonometric Identities, or the Identities of Trigonometry. Thanks for viewing.